All right, so we're going to pick up sort of where we left off last class. We were discussing calorimetry, and that introduced us to this form of energy that we started talking about. Our first introduction to energy in this course, what we called thermal energy or heat, and how if an object absorbs heat, absorbs that thermal energy, we can measure that by an increase in the temperature of that substance. Likewise, when something cools down, when something decreases in energy, in temperature, that's because it's losing that thermal energy. Okay, so we're going to discuss thermal energy some more today. All right, but in the topic of what's called thermodynamics. Thermodynamics is a big topic in chemistry. Thermodynamics is all about energy exchange in a chemical process. All right, so the absolutely bonkers thing about thermodynamics is it is a field that we very much so still study today, but the foundation of thermodynamics was laid out in like the early 1800s, late 1700s. It's one of the oldest branches of chemistry, which is just mind-boggling because they didn't have anywhere near the technology that we have nowadays. They didn't even actually have proof that atoms existed yet, and they were still able to nail down the tenets of this theory here. So, pretty cool. Energy is a fundamental aspect of a chemical reaction. What we're going to be studying with regard to thermodynamics is that one specific type of energy that we've been discussing, thermal energy. All right? In Chem 1B, you'll be introduced to a few different types of energy that pertain to chemical reactions. We're going to very much so focus on what's called enthalpy. Enthalpy, we use this delta H symbol for here. All right, and again, enthalpy measurements are exchanges of thermal energy in a chemical process. All right, so we're going to be talking about chemical reactions and this enthalpy change that we observe, which is how much thermal energy is either released by that chemical reaction or absorbed by that chemical reaction. All right, so many reactions, most reactions, will actually release heat as that reaction is occurring. There are a few reactions out there that will actually absorb heat as that reaction is occurring, right? But the chemical reaction itself is going to be either releasing or absorbing thermal energy, and again, we call that enthalpy. All right? And I keep on saying we're going to talk about exchange of energy, exchange of energy. What the heck do I mean by that? Well, importantly, thermodynamics, we have these theories that are so fundamental. Nobody in the past 200-300 years, whatever it is, has been able to find any sort of a flaw in these theories. So they're so fundamental that we call them laws in chemistry. They kind of like bump up to this next level of importance. And what we're going to introduce now is the first law of thermodynamics. All right, and that first law of thermodynamics is what we call the energy conservation law, or the idea that energy cannot be created or destroyed, only transferred. All right, so we are sitting at a finite amount of energy in this universe. There's no new energy coming in, there's no energy going out. Every bit of energy that we have is all here. What's being happened is being transferred from one form to another. So for example, our star at the center of our solar system, the sun, is a just big ball of a crap ton of energy. And it's sitting there and releasing that energy constantly throughout the solar system. We take that here, and really our plants, right, they do a great job of harvesting that energy and turning it into food for the plants, right? Sugars that help the proteins, all this stuff that helps those plants grow. We take that energy, we eat it, we convert that into energy that powers us and our beings. It's still a finite amount of energy, right? So it's only being transferred from the sun to the plant to our food, et cetera, right? So we have a finite amount of energy in this universe. It's just being transferred from one form to another. And this is a chemistry class. So what are we really interested in terms of these transfer of energies? Our transfer of energy from our reactants to our products. All right, and again, that process, that chemical reaction, will release or absorb heat, will release or absorb thermal energy. And there are other forms of energy at work in these chemical processes, but we're very much so focused only on the thermal energy picture for right now, what we are going to call enthalpy throughout this course. All right? All right, so let's talk about a very simple chemical process here, not even really a reaction, but one of those phase changes that we were discussing. If we take, for example, liquid water, and we turn that into solid water, or what we would call ice. Okay? This right here would be a process that we would call what? When liquid, we go from liquid to solid? So this would be freezing. All right, so let's think about this for a second. If we're going to freeze water here, are those liquid molecules, those liquid water molecules, are they going to have to absorb or release heat? Right, so they're going to have to, they have too much energy. In order to get, they're moving around all happy-go-lucky in that liquid phase. In order to get in the solid phase, they have to lose that energy. They're going to get stuck in a certain place, right? They're no longer as freely moving. So this process here is one that will lose thermal energy. Or release. Let's use that same terminology we introduced last time. All right, so we are going to be talking in terms of this enthalpy concept here. So we have some fancy terminology for a chemical process that releases thermal energy. Okay, a delta H that is less than 0, a negative delta H. This is a chemical process that releases thermal energy. We call this exothermic. So a chemical process that releases thermal energy, we would call that an exothermic process. All right, so our freezing here, again, we call exothermic because this is a process that releases thermal energy. All right, but then we can take that solid ice and put it into a warm environment where it then melts, going the opposite direction here. All right, this would be a process not that releases thermal energy, but absorbs thermal energy. All right, we got a fancy term for that as well. If a process is absorbing thermal energy, that means that the delta H is positive, greater than 0. And we call that an endothermic process. All right, so we have fancy terminology here, reactions or any chemical process. In this case, it's a phase change, not a reaction, but the process that releases thermal energy will be what's considered an exothermic process. All right, a reaction that absorbs thermal energy is what we call an endothermic process. All right, that corresponds to the sign of that delta H value, right? We talked about how when you talk about energy, that value for Q that we looked at last time, the sign tells you whether that energy is coming or going. A negative delta H is one that releases that thermal energy, or an exothermic process. A positive delta H is one that absorbs thermal energy, or an endothermic process. All right? All right, and there's one thing about this value, this delta H, that makes it really, really convenient, and that is it's what's called a state function. Okay, state function depends only on the starting, which would be our reactants, and endpoint, which would be our products of a reaction. All right, this is a little weird at first, but we're going to see why it's super convenient here in a second. All right, the bottom line is a chemical reaction will release the same amount of thermal energy if you do it in like one step or if you break it up into a bunch of different steps. The only thing that will dictate how much energy is absorbed or released is the starting point of that reaction, your reactants, and the end point of that reaction, your products. It doesn't matter what happens in the middle. How your reactant gets converted to product is irrelevant from an enthalpy standpoint, from a release of heat standpoint. All right, so a better example of this is taking some physics quantities, because these chemical reactions and energy, it's hard to picture here, but let's imagine that we have this mountain range here. All right, and we got two hikers. We got the red hiker and the green hiker. And we're going to start them both at the exact same point. All right? Our green hiker is a beast, just super fit. They're going to beeline it straight up to the tippy top of that mountain. That's going to be our end point. All right? The red hiker, not into that incline. All right? They're going to take the switchback route, and they're going to go the back and forth and back and forth. Nice leisurely walk up to the top, but still going to end at that same point. All right? So one of them took the very direct route, expending a lot of energy, having to go up all that incline, but then it's over a shorter distance. The other one took the easier route, right? Less incline, but longer distance. All right? So in terms of the distance traveled, all right, which hiker took the longer distance, the longer path up that mountain there? My red hiker, right? So red was longer than the green path. All right, and that's because distance is what's called a path function. All right, the distance traveled very much so depends on the route that you take. But there's another quantity in physics that's very important, what's called displacement. All right, and displacement is simply the difference between the start and end points. And so in terms of the displacement of these two hikers, since they started in the same place and they finished in the same place, they have the same displacement. Displacement is an example of a state function. A function that depends only on where you start and where you finish. All right? Enthalpy is also a state function. For a chemical process, it only depends on where you're starting that chemical process and where you're finishing. Doesn't matter what happens in the middle. The details of how this reaction is occurring is irrelevant from an enthalpy standpoint. All right, so that becomes super duper useful from a scientific standpoint. Scientists have taken advantage of this by tabulating enthalpy values for specific types of reactions, but then we can combine those tabulated values to figure out the enthalpy of any reaction. All right, so that's what we're going to do here. These are what are called formation reactions. Okay, so for a formation reaction, what you would do is you would take any compound formula here. So for example, let's do MgCl2, which is a solid. All right, if we're going to take so this is our any compound that we want here. All right, the formation reaction, that compound is going to be the product of these formation reactions. And our reactants are always going to be all the elements that we see in that product. So the magnesium and the chlorine in their standard states. All right, we were doing these formation reactions. These were sort of the first types of reactions that we were introduced to when we were converting these sentences into these balanced chemical equations. It would have been like, take magnesium and chlorine to create magnesium chloride, and you guys were drawing me balanced chemical equations of those reactions just from that description. Right? And the way that we were able to do this is using our periodic table. We can say, all right, magnesium in its standard state, meaning it's all by itself, not in a compound with anything else, so just magnesium metal. And magnesium metal is a solid in its standard state, which is why it's in black on our periodic table. All right, so then my other element is the chlorine. Okay, and it's been a minute, so let's remind ourselves. Chlorine is one of these 7 special elements on our periodic tables. All right, when we draw our formula, what do we got to do? It's not just Cl, Cl2. It's one of these diatomic elements. And it's a gas because it's in red on our periodic table here. Okay, just because it's been a minute, let's remind ourselves here. What am I talking about? We have these 7 diatomic elements. Okay, they make a little 7 on our periodic table, all nonmetals. All right, but that's only 6. What's the other one that I'm missing? It's always on the wrong side. Our other nonmetal hydrogens. So these are 7 diatomic elements, meaning in your standard state, they appear in pairs. So oxygen, for example, when you write your molecular formula for oxygen, it's not just O by itself, but O2, and it's a gas in its standard state. All right, so every element in their standard state combining to make your compound, that's what we call a formation reaction. All right, so the other important thing about formation reactions is they're balanced a little weird. All right, you can see non-integer values in your balancing because the goal is always to have a 1 on that product side. Okay, so for example, the formation reaction of sodium chloride. I'm again going to do each element in its standard state. Sodium in its standard state is just sodium metal. All right, but again, chlorine is diatomic in its standard state. But if I just left it as is, this wouldn't be balanced. All right, we're always going to balance these in such a way that there is a 1 on this product side. All right, that's going to make it more useful. So we're going to break our balancing rules here. We're allowed to have non-integer values on our reactant side when we balance. By that I mean I'm going to have to put a half out front here to balance my chlorines. And that's okay, specifically because it's this formation reaction here. And I'm trying to keep it a 1 on my product side. All right, cool. So then everybody take a second and give me the formation reaction for calcium oxide here. All right, so calcium in its standard state is just solid calcium metal plus oxygen in its standard state. Remember we said oxygen was diatomic, so it's O2 gas. All right, but I can't be done here because this isn't balanced, and I'm going to balance it specifically so that there's a 1 on that product side. So in order to do that, I'm going to need to put the 1/2 in front of my oxygen here. All right, let's do 2 more here. We're going to do liquid water and gaseous water. All right, water vapor. All right, so I look at those 2 elements. I need hydrogen in its standard state. Hydrogen is also diatomic, so that's H2, gas. My other element, my oxygen in its standard state, is also diatomic and gaseous, so plus O2 gas. But then I need this balanced in such a way that keeps that coefficient of 1 on my product side. So again, I'm going to put a 1/2 in front of that oxygen. All right, if I look at my second formation reaction, my product is different because now I'm talking about water vapor. But when I do my formation reactions, I'm going to take hydrogen in its standard state and oxygen in its standard state. So my reactant side for that formation reaction is the exact same. Right? All you're doing is taking each element in its standard state. So if I have the same elements in both of my compounds here, regardless of the fact that they're different states of matter, that doesn't influence how I build my formation reaction, right? Elements in their standard state coming together to make whatever your compound is that you're trying to look up. All right? All right, so what is all this all about? Like, why are we talking about these formation reactions here? What is this doing for us? All right, so let's say that we want to calculate the enthalpy, that delta H value. And we're going to look at that process that we were talking about at the very beginning of class here. If we take liquid water, oh, did I do gaseous? Okay, whatever. Liquid water and convert it into solid here. And we had our predictions about what that value for delta H with the sign of that delta H is going to be. But now let's say we want to actually calculate it here. Let's put a number to this. What is the delta H of this process here, the enthalpy change in this process? Okay. Well, we have these formation reactions that we were talking about. All right. So we're going to look at the formation reaction of our reactants and our products here. Okay. As we said, the state of matter is not going to influence our formation reaction. We're just going to take our elements in their standard state. So we looked at these previously, hydrogen gas, and then the oxygen gas, but I'm going to balance with the 1/2. All right, and then we'll take the formation reaction of our product, that's solid water. All right, so what's so special about these formation reactions? Well, scientists just did a whole bunch of these formation reactions. And they went in and they measured the enthalpy change, the amount of heat that was absorbed or released for all these different reactions here. All right, so what we're going to have on our constants page for this chapter is this appendix here, this list of a bunch of different compounds, right? So for example, barium chloride, I could look that up. And for each compound, we can see the delta H of that formation reaction is listed. There are these other ones here that we're going to ignore until you all get to Chem 1B. All right, there are other forms of energy involved in chemical reactions. We're specifically talking about that thermal energy, the enthalpy, so we can ignore these other two columns here. But this first column here will give us the enthalpy change, and that corresponds to the formation reaction of that compound. All right, so we were talking about water. So let's scroll down here. It's listed by element. So we're going to look, I guess it's under oxygen. All right, you're going to have fun hunting around on this page until you get used to it here. Elemento. There we go. All right, so we have liquid water here. Okay, so again, we're going to look up that delta H value, and we see it has this negative 285.8 number. All right, so that corresponds to the formation reaction of that liquid water. What that tells me is that the delta H of this reaction here is that negative, I don't remember what I said, 238, something like that. Negative 285.8. All right, and I'm just now realizing there isn't solid water on that table, so we're going to instead look at a different phase change here. We're going to switch this to gaseous water. Okay, so we're not talking about freezing anymore. Sorry about that. And we're going from a liquid to a gas. What process are we looking at here? What phase change? Going from a liquid to a gas, this would be the boiling of water here. All right, so then we look up that compound, our gaseous water. When we go to our constants page and we look up that value that we see for gaseous water is, again, the formation of the enthalpy of that formation reaction, negative 241.8. All right? And if I'm being good and I look at my units here for that value of H, we see that our delta H values are listed in terms of kilojoules per mole. All right, so let's be good and put our units on those values. Kilojoules per mole. So for every mole of liquid water that's formed, that reaction, that formation reaction, would release 285.8 kilojoules. And if instead you did this formation reaction and formed gaseous water, it would release 241.8 kilojoules, right? So those values that we look up on those constants page correspond to these formation reactions. All right? So that's one particular reaction that we have this enthalpy for. But again, we're going to take advantage of the fact that our enthalpy is a state function. So it doesn't matter where I start or where I stop. I can still calculate the change in enthalpy of that value. All right? So what we're going to imagine is if instead of doing this in two steps here, or in one step here, going from our liquid to our gaseous water, we're going to first go from that liquid water to those standard state products, to our standard state elements here. And then we'll take those and combine them into that gaseous water. All right, so this is what we're kind of imagining that we're doing here. All right. Well, we know, based on what we see above, this reaction right here, taking that hydrogen gas and that oxygen gas and creating that gaseous water, we know that this process has a delta H of negative 241.8, and again, we'll be good, kilojoules per mole. Okay, so then if we look here, this first step is going from liquid water to these compounds, these elements in their standard state. So the reverse of what we see up here. All right, so importantly, if we have, let's just do it side by side here. If this is our reaction, and we know the enthalpy is this negative 285.8. If instead we looked at the reverse reaction, we switch these around, well, if that reaction above released that 285.8 kilojoules per mole, this reverse reaction here would absorb 285.8 kilojoules per mole. Right? So I took my chemical reaction and I did the reverse. So that means I took my delta H and I multiplied it by -1. I flipped the sign of that delta H, right? This is the same process. You're just starting and ending in a different place, right? So you're starting instead with the liquid water and ending with those elements in their standard state. So this is now going to absorb that same amount of energy. Okay, so that means that I know that this process, this first step here, has a delta H of positive 285.8 kilojoules per mole. Okay, so then in order to get the delta H of my overall process, again, it doesn't matter that I broke it up into these steps. I can still figure out my delta H by looking at the value at each one. So I'm going to take those and sum them together. My 285.8 plus the negative 241.8 All right, and I'd get a delta H of this reaction of positive 44.0 kilojoules per mole. All right, so where we have is this reaction. It's really a process here, the boiling of water. And I was trying to find the delta H of that reaction. All right, and so what I did is I looked at my constants page, and I have a bunch of these delta H values that are tabulated. But they're for a specific type of reaction, what's called a formation reaction. So I looked up my reactant, got its formation reaction, right? Then I looked up my product, I got its formation reaction, and I have the change in enthalpy of both of those formation reactions. Right? I can use that as pieces of information together to figure out my change in enthalpy of my overall reaction by imagining that I break it up into these steps. First, I take my reactant and break it up into those standard state elements. And then I take those and combine them back. And again, our change in enthalpy, it doesn't matter what we do in the middle here. It only matters where we start and where we end. So using those two values together, I can find that my change in enthalpy for my reaction is positive 44.0 kilojoules per mole. So what can I say about this reaction here? Is it absorbing heat or releasing heat? So this would be absorbing heat, and that kind of checks out from a, if we think about it standpoint here, we're taking these liquid water molecules and then promoting them to the gas phase, right? We need to put energy in to those liquid water molecules so they can break free and start floating around in the gas phase here. And on a process that absorbs thermal energy is what we call an endothermic chemical process. All right, and we can, we approve that by looking up those values on our constants page here. Okay, so we can do this for any chemical reaction. We can look up those values for those formation reactions and use them to calculate the values of any reaction, of the enthalpy change for any reaction. All right, so we can kind of simplify this here. We don't have to go through the process of writing out those chemical reactions every time. We know that they correspond to formation reactions. So when we're trying to calculate our delta H of a reaction, we're going to go to those constants page and we're going to look up those values. And what we're going to do is we're going to take the sum of all of the delta H's of our products, and we're going to subtract the sum of the delta H's of all of our reactants. Okay? When we do that, so first of all, this little big uppercase E here is really an uppercase, what is it, sigma? It doesn't matter. Letter of the Greek alphabet. This means sum up all of those different values. Those delta H of your products, this is the delta H that you look up from our constants page. All right, but then you also have to take that delta H and multiply it by the stoichiometric coefficient from your balanced chemical equation. All right, so when you go to that constants page and you start calculating your enthalpy, you're going to remember this one phrase that you're going to chant to yourself: products minus reactants. Products minus reactants. That's what we got to remember. We got to take those values that we get for our products, sum them all up, take the values that we get for our reactants, sum them all up, and we take products minus reactants. That's how we use that constants page. All right, and we talked about why is it minus your reactants, because remember, you got to take that formation reaction and reverse it, which means that you take that delta H value and multiply it by -1, right? So you subtract the delta H of your reactants. All right, so then let's use this here for another chemical reaction. Let me see what we have here. Cool, all right. So let's look at one of these combustion reactions. So that would be if we took methane plus oxygen. We always have the same two products for our combustion reactions. What are those two products? CO2 and water vapor. All right, everybody take a second and let's balance this chemical equation here. Okay, so then what I'm going to do is I'm going to go to my constants page, and for each one of these compounds in my chemical reaction, for each one of these, I'm going to look up that delta H value. All right, for all of your products and your reactants, you're going to look up those delta H values. So I need it for the CH4, for O2, for CO2, and for H2O, specifically gaseous H2O. All right, we're going to get the delta H for each one of these compounds. Okay, I guess we did it for water, right? For gaseous water, negative 285.8. These are all going to be in kilojoules per mole. Okay, so let's look it up for each one of these compounds here. So we have methane, that negative 74.6. Carbon dioxide should be around here somewhere as well. Yep, negative 393.5. All right, and now we need to look it up for oxygen as well. Okay, we see that our formation reaction enthalpy is 0 for this oxygen. That's because your formation reaction for O2 would just be starting out with O2 gas, going to O2 gas. That would be your formation reaction. So what you'll see is every element in their standard state, when you look up their value on that constants page, has a delta H of 0. Okay, so now we can use these values here to calculate the delta H of our overall reaction by taking your products minus your reactants. All right, you just have to remember to multiply those delta H values by a stoichiometric coefficient. So that value for water, you'll have to multiply by 2. Carbon dioxide, it's just 1, all right? But don't forget those stoichiometric coefficients. So everybody take a second, see if you can't calculate the delta H of this reaction.
Wouldn't H2O gas be negative 241.8?
Did I grab the wrong one? Oh yeah, sorry, I grabbed the wrong one. Negative 241.8, thank you. right? So I take my reactants, or I take my products. I'm going to take the delta H of my CO2, and then I'm going to add 2 times the delta H of my H2O. That gives me my delta H on my product side. I'm going to do the same thing on my reactant side, sum those all up, and then I'm going to do products minus reactants, which would get me a value of negative 802.5 kilojoules per mole. So is this reaction endothermic or exothermic? Exothermic, right? And these combustion reactions, right? That's what takes place in your car engine. If you have a lighter, that's a combustion reaction, right? We could call these burning reactions. These are reactions that release a lot of heat, right? So they are indeed exothermic reactions. Importantly, we can calculate the delta H of any reaction by looking up those values on our constants page. All right, we'll pick up with this next time. The constants page will be on campus. I'll open up that module later today and you'll find it on campus. How's it going? I know where it is. I don't have it yet, but I did track it down. They just delivered it to the wrong office. Okay. But yes, I'll get that graded and get that put in. Products minus reactants. You have it flipped around. Products minus reactants. Yeah, and then look, the other thing is when you do swap it, to keep that minus sign correctly distributed, you're going to need to put that in parentheses. Right? On your products minus reactants, put your reactants in parentheses to keep your order of operations straight. Cool. What up? You ate a bug?
Yes.
Gross.
I
Bummer.
was walking, and the bug hit my coffee cup. So of course I examined my coffee cup to make sure it's not in there.
Of course.
And then I go to bite my snack, and I'm tasting a bug. Next thing I know,
Yeah,
it was
that's a bummer.
disgusting.
It's good protein. Good protein.
It's disgusting.
Yeah, that is a bummer.
And then I almost got kidnapped on like Saturday. It's crazy.
You almost got kidnapped?
Yeah. Somebody pulled up to the side of the road and was like, "Do you need a ride?" And I was like,
Oh.
"Ooh."
Is this at that event that you were at here?
I went to Vintage Yard.
Yeah.
And then I was walking home, and I was like,
Sketch.
so I missed them out.
Sketch for sure.